Welcome back. This is 9.2. This is the last section of problems. I'm going to be talking a little quieter today, or not today, but for this last video because people are asleep in my house. So let's get going. First one. This is in Yellowstone National Park. The wolf population is dependent on a large, strong moose population. Let X be a random variable that represents the fall moose population in hundreds in Yellowstone. And let Y be a random variable that represents the late winter wolf population. That one doesn't say in hundreds, so just be aware. A random sample of recent years is given. Create a scatter plot for the given data. Okay, so I actually did this already, and the way I graphed it just with the baseline numbers, not including the hundreds. If you wanted to, you could have changed this to, add the 2 zeros for each value if you wanted to. But you'll see actually either way it's not really important as long as I keep in mind when I answer any questions that these are actually those 2 extra zeros. Okay, why does my line look like that? Well, because in contrast to my relatively small y's, the x's are huge, right? So everything is like getting really spread out. How can I adjust for that? Well, I can just adjust by changing the domain of my x-axis. X-axis, let's start it from, what's the smallest value? 1700. Let's start from 1500. And then I can change it to the highest number is 3400. So let's say 3500, something like that. And meanwhile, the y-axis starts, the smallest value is 48, it looks like, so I can change that to, let's say, 45. And then the largest value is, what is that, 79, so let's say like 80, 85. And you see I basically cover the same shape, but really hidden here is the fact that the scale is really different, right? Like near the bottom, you see this is 2000, this is 2500, so this gap here represents 500 on the bottom. Okay, but like I said, actually, let's take a look at what happens real quick. So let's recalculate this. All right, what do we see? We see that B is 21.307. So that's what we can expect when there are 0 moose. And M is equal to 0.015162. So we have a really tiny slope. Tiny slope because we're going really large x values and really small y values comparatively. Our R value is 0.8117. So a pretty strong correlation here, right? Okay, let's see what happens if I delete the zeros here. Come back to the original star. I can just graph, keeping in mind when I answer questions that really 30 represents 3000, yeah. Okay, and I just recover basically the graph if I just scale my axes properly. So I can do that by, again, clicking this arrow, this toolkit here, the wrench, y-axis. Oh, I should have kept the y actually, but let's adjust it a little bit. Let's say y is from 0 to, my largest value is 70, so let's do 100. And then x value, let's also do 0 to 100, see how that looks. Just to adjust my screen, yeah. Okay, that looks pretty good. That gives us a pretty decent picture. And now actually everything is square, so we have a pretty decent picture of how they're related. You'll notice my slope change. It was 0.0 something, now it's 1.5. So pretty much it's just changed by a factor of 100, right? Multiplying or dividing by 100. All right, let's go and answer the questions. By the way, this problem where I got this idea for this question is because I was listening to a podcast called This Is Love, which I recommend. The latest episode was about wolves in Yellowstone. It's really a tragic story because back in the day when Yellowstone was first opening, they had this kind of negative view of wolves. So they ended up decimating the wolf population purposely. Later on, they realized their mistake and how it had disrupted the ecosystem, and they reintroduced wolves. And anyways, the story that I listened to, this is called, it's the newest episode on This Is Love. This is the podcast name. And they talk about this particular wolf family. It's really interesting and it's pretty touching too. So anyways, So here we created a scatter plot already just by plotting the values, right? For you, if you want to do it on your calculator, you go to Stat, Edit, Make Your Lists, Stat, Calc, and hit the regression, and then you can enter your two lists, and it'll pop up basically like this. So we did that. The correlation coefficient was at R that popped out, and you notice R is the same whether we included the zeros or not. That's because R is just telling you if the things are related or not. And 0.8117, that means it's a strong linear positive linear correlation between the number of moose and wolves. Okay, what's the equation? So the equation is y equal to mx plus b, where m is the slope here. If you're using our calculator, they denote m by a instead, but it means the same thing, it's the slope. And then b is the y-intercept, so in our case 21.307. Now that would be how many wolves you would expect if there were 0 moose. However, that would be pretty far outside of the range of things that we could guess, right? For 0 moose, we don't have a good way of estimating based on the linear regression because that's far outside of the values that we have. X values, the smallest one is 17, the largest one is 34. So it's got to be somewhere near those to make a proper estimation using this regression. Okay, letter E. What's the predicted size of the wolf population if the caribou population... Oh, I'm sorry, this is a typo. Oh, this should be moose. The moose population is 3,600. Is this an interpolation or an extrapolation? So first of all, let's figure out where does 36 lie. 36 is outside of our range, right? 3,600. Okay, so first, to answer the first question, or I guess the second question, this would be an extrapolation. And let's now backtrack to answer the first question. What is the predicted size? 36 is within reasonable range of where we are, so we can make a prediction here. And what we're going to use is we're going to just use this formula here. Y is equal to 1.5162x plus 21.307, where x is just that moose number, right? The number of moose. So I'm just going to fill in that with 36 and see what pops out, and then that will be my answer. So in fact, let's just pull up this calculator right here. Doing a new equation. So under 1.5162, I guess I didn't need to, I could just type this in. 1.5162 times 36 plus 21.307, and I get 75.89. Alright, so what's the predicted size of the wolf population? Let's round it to the nearest wolf because it doesn't really make sense, I guess, to have half wolves. If you said 75.89, I wouldn't fault you for that, but let's just go to the nearest wolf. When you do your homework, just pay attention to what they ask you to round to. Let's say 76 wolves then, right, to the nearest wolf. 76 wolves. And it's an extrapolation. Just to recap, how do we get that? We're using this formula above. So I'm just inputting the x value that I'm given, 36, into the equation. That's all. And that's equal to 76. So 76, roughly 76. So since it's rough, let me add the tilde. It's about 76. Let's answer the next question. If the actual size of the wolf population is... Oh, sorry, this is typo 2. It should be 81. 81 when the caribou population is 3,600. Then what is the residual? Alright, so all that is the residual is just the true value minus the estimated value, right? Which is 81 minus 76, that is 5. So 5 wolves. The residual is 81 minus 76 equals 5 wolves. Alright, what is the predicted size of the wolf population if the caribou... Oh, sorry, this is again mistake. This should be moose. I changed it because I changed it around caribou to moose, which is kind of unnecessary. I could have just kept the caribou, but whatever. I know there are moose in Yellowstone. I'm not sure about caribou. Is it the same thing? Never mind. Okay, what's the predicted size? 4,500. That would be 45 using our scale, right? So I'm going to do the same thing as before. This time I'm doing an interpolation. In fact, I should ask that question. Is this an interpolation or extrapolation? So to answer that second question, it is an interpolation. Okay, what about the first question? Well, I'm just going to use that same formula. Y is equal to, stop it. Y is equal to 1.5162, this time times 45. But, oh, wait a minute. I was looking at the wrong values. 45 is outside of the range. I was looking at the right side. So 45 is actually well above our biggest value, which is 34, right? So actually, we want to say in this case, no conclusion can be made. No conclusion can be reached using a regression line. That's because the value 4,500 is outside, is both outside of the range and it is not close. That's pretty worded pretty badly. Let's write it this way: is neither inside the range of values, neither within the range of values, nor is it close to the range of values. Not the best wording, but you get the idea. Okay, so we can't make a prediction because 45 is outside of our, not only is it outside, but it's far away from everything that we have. Okay, that is that question done. Let's move to the last question. Right, the distance a mountain or island is from Kilauea is related to its age. The following table shows the distances of different mountains or islands and their age in MA. MA stands for hundreds of thousands of years. I guess that's because like the hot spot, right, for which form the Hawaiian Islands, as the tectonic plates shift, then new islands are created. So if the oldest one is Kilauea, oldest volcano, then as time progresses, things get farther and farther away in theory, right? Now maybe things might circle back because it's not exactly a linear direction, so that might not be perfectly true, but roughly speaking. Okay, so first it says to create a scatter plot, so we're going to do the same thing, just input our data. And if you're using the calculator, then make your two lists, right? And then you're going to do StatCalc regression. But I'm going to use this Desmos calculator again. First value is 54, then 182, 226, 280, 339, and 519. Alright, this side is 0.38, 0.75, 1.28, 1.9, 2.6, and 5.1. Okay, notice our line looks pretty miserable. That's because our range is again kind of off. So I'm going to click the wrench again. Let's look at our x value. Smallest value is 54, so let's start it from about 50 on the x-axis. And then if you don't have to go through this process if you're doing it on your calculator, because I think it automatically adjusts to fit the screen properly. But for us, I'm using this one, so 519 is the largest. Let's go up to, I don't know, 550, say. Okay, that's looking pretty good already. And the y-axis, let's adjust similarly. Smallest value is 0.38, so why don't we just start at 0? And then the largest value is 5.1, so let's say, I don't know, 10. And let's just shift it a little bit. Okay, sweet. So that's the picture here we get. Here's the regression line. Here's a scatter plot. Part A is done. Scatter plot are those those green, I don't know my colors, green dots. Correlation coefficient, that's just this R value that pops out. So, oh, this one is nicely correlated, 0.9697. So that's a very high value, right? So just like the previous question, actually, we have a high positive value, which means, how do I interpret? There is a strong positive linear correlation. And to be more specific, between the distance landmarks, let's just say, are from Kilauea and the age, those landmarks. Formatting's weird here, sorry about that. Okay, now find the equation of the least squares line. That's the regression line. So I'm looking at here, this guy, y is equal to mx plus b, and I'm just going to input my m and my m and my b. So it's going to be y is equal to 0.0105898 x plus b, which is negative 0.822274. Okay, next part says Niihau is 359 kilometers from Kilauea. So at that distance, what is the expected age of? Oh, sorry, another typo. I changed that. This is to Niihau. I'm going to update this when I send it to you guys. Okay. At that distance, what is the expected age of Niihau? So all I'm doing is I'm just inputting that into the formula I wrote above. It's going to be y is equal to 0.0105898, and this time x is, what was it, 359, and then add negative, or you could just say subtract 0.822274. Okay, let's type that in, see what we get. 0.0105898 times 359 and minus 0.822274. All right, what I get 2.9794632. Let's just round to the nearest first decimal place. So if I round to the first decimal, that means that's going to round up to 3.0. Actually, no, let's do 2 decimal places because these other guys over here are to 2, yeah? So let's just do 2.98. Okay, that's MA. Alright, to predict the age of Niihau, did we interpolate or extrapolate? Well, that was 359. That is inside of our range, right? Our highest value is 519, lowest was 54, so that means we interpolated. Okay, no, according to Google Sensei, Niihau is 5.5 MA. Our predicted value is 2.98 MA. So what is the residual? It's just the difference of those two. So it would be 2.98 minus 5.5. Our observed value, I'm sorry, wait, I got this backwards, sorry. It's the observed value minus the predicted value. Predicted value here was 2.98. So let's calculate that. 5.5 minus 2.98, which is 2.52. So we were way off in the prediction. Okay, so there it is. 5.5 minus 2.98 is 2.52 MA. That's the residual. I feel like, did I put the right order here? Let me just double check. Okay, so the actual wolf population was 81, and we subtracted the predicted value there. So we did that in the right direction as well. Okay, that was okay. So this one is also correct. Okay, then that is it. We're done. It's kind of sad I'm not going to be making any of these for you guys anymore. Although actually I might, because once we start the project, I do want to show you some other tools using StatCrunch. So that's a possibility. We'll talk more about that next week though. Okay guys, have a good one. Stay safe. See you later.